Okay, in this unit, we're going to look at some standard classification methods. So most of these have been around for a while and kind of considered standard statistical or artificial intelligence methods. They do involve some machine learning, but again, they're more traditional methods. Later on, we'll move on to like neural networks, which are a newer model and often considered more machine learning-like. So these are classification methods. What that means is we have a set of inputs, usually numerical number inputs, some measurements or something like that. We feed them to our model, our classification model, and we predict a class. So unlike regression where we're predicting a number, we're giving out a decimal number, a real number. Here we're predicting a class. Like this image is a dog and this image is a cat, or this cancer tumor is malignant or benign. That sort of classification model. There can be a number of classes, it can be just two or many classes. These are supervised models in that we are given a whole set of data with this. So we're given a bunch of examples with the inputs and the actual class. And our model learns or fits the model based on all this data we're given for it. So the first method is nearest neighbor. When we're looking at data, we can often look at the nearest neighbor. I'm going to go into this animation and look at it. So let's say we have this animation here. We have two categories, oranges and green apples, for example, here. And we have some measurements here. Maybe one is the bumpiness of the fruit and the other one is the color or something like that. So we have two different measurements here. And we have some new measurement coming in here. And we want to know, is this an orange or a green item? Which class does this fall into? And so what we can do is look at the neighbors of this. And so we can kind of look at these neighbors and see. So we can start by just looking, around it and keep kind of looking nearby at the closest neighbor. So if we kind of expand this circle, we can see the closest neighbor we get is this orange. So if we look at the one nearest neighbor, it's orange here. And so that's what we often call just the one nearest neighbor. We just look at what's the nearest one to it and classify it here. So like again, in this sample, here's our iris samples plotted with the petal length and the petal width here. And if we have this new sample, we can kind of look and see, obviously the closest one is a blue here, which is a setosa, iris setosa. So this one is likely a iris setosa also for this. Now, sometimes we want to look at more, it's worthwhile looking at just the nearest neighbor because again, we might have an anomaly here. So you might have one here and the nearest neighbor is a green, but if you look at more neighbors, it's really most likely an orange if it's down here. So there's just some anonymous value there. So we'll look at often like 2 or 3 or 4 or 5 nearest neighbors, 10 nearest neighbors here. So let's look at the 3 nearest neighbors for this. So again, if we're in this sort of model, we can kind of expand our circle, our nearest ones, and then at this point we see we've got orange near, and then we have a green and another green. This orange is a little further away than this one by our circle here. And so we've got 3 here, and so we can vote. And so we have 1 vote for orange and 2 votes for green. So with 3 nearest neighbor, we'd say this one is a green now for this. And because we're voting, we often do nearest neighbors with an odd number, just like you see on judges on or jury numbers. Anywhere we're voting like that, you'll have an odd number so that you don't tie as often here. So again, we can look at this one. And we can look even at this inner circle it looks like a green, an orange, and an orange. So we have 1 green, 1 vote for iris virginica, and 2 for iris versicolor here. And so if we're looking at the 3 nearest neighbors, these all vote, and our result would be sample 2 would be a versicolor. So we generalize this rather than just saying 1 or 2 with putting a K there and say K nearest neighbors, and then we can set what K is. So there's another article that links in here. One thing that's nice about this is it's pretty easy to understand, and it's quick to calculate the distance between points, and we can do this in multiple dimensions. Here we're just doing it 2 dimensions so we can visualize it, but this generalizes to any number of features we want. One problem is that it is slow for large data sets, because every time we get in a new point like this point here, even though it's quite obvious to us visually that it's a green, the algorithm still has to compute the distance from here to every item, every sample in our thing. And here there's only 150 iris flowers. But again, if we have 100,000 samples, we have to do that distance to 100,000. So there's ways of doing that sometimes to try to average them and do things. But again, just the general k-means is slow with large data sets for that. Also, the size of k for most places, like here, if we have k is 1 or 3 or 5 or 21, it'll all be green here. But in other areas, the hard to decide ones, the choice of k will change the results for this. And that's what we saw here, is that when we're looking at just one nearest neighbor, it's orange. When we're looking at 3 nearest neighbors, it is green. But if we go up to like 5 nearest neighbors or 7 nearest neighbors, then it's 7. Then it's orange again. So it's again, that is sometimes confusing for people to try to figure out what's the right k to pick. Okay, so that's k nearest neighbors. So another way we look at it is that, well, rather than doing that, can we just draw lines through this and say anything on one side of the line is this color, everything on the other side is another color. So that's what we're doing with support vector machines. We're going to try to draw this line in here for it. So again, the idea, if I look at this visualization, is that we have a bunch of orange and a bunch of green samples here, and we're going to try to draw a line that divides this sample. And so again, we can tweak some things where the line is and what direction the line goes, and play with these parameters. And again, there's some nice mathematical ways of doing this. Now, if we have a couple lines here, like there's a line there, and we can also have a line there, or there, which line is better? So how do we decide one line better than the other? And what we generally do is we try to look at the path around it. How big of a path around it do we get before we bump into some of the samples here? So we call this kind of the decision boundary, and so we try different lines and see how wide of a decision boundary we have. But then if we can kind of move this in different ways, we can maybe get a wider. So now we can widen out the decision boundary some more. So this is a better solution because we have a wider path. And again, maybe we can tweak this some more and move this around so we can get even a wider decision boundary. So again, what is the path here that we can set up to get the widest decision boundary in here? And there's some nice math that goes into calculating this that we don't need to deal with here. But that's what support vector machines. Here's back to our iris flowers. Again, we're looking at these different lines that can be drawn in here. And again, we want a line where we can maximize this decision boundary in here. This is this is called linear support vector machines. It only uses straight lines. We talk about what is called the kernel, and that's the what type of line we can have. So linear ones will use straight lines. There's also a couple different ones. A common one is radial basis function, which uses a kind of curved line in here for this, and that's a type of kernel we can use. So when we're doing support vector machines, we can specify the kernel, either linear or RBF. There are other ones, but those are the only ones we're going to look at that are pretty common. The other thing is that sometimes our data is such that there isn't a clear line for this. So like if we are trying to draw a line through here, the oranges and the greens here overlap. So there isn't a best, a line that totally separates them. We're always going to have some on the wrong side. So how bad is that? Now, if we allow some curve in here, we can get a really twisted line in here, a curved line that might do that. So with RVF kernel, we can do that. The question is, how much penalty do we pay for having misclassifying one of the objects with our line? And so there's a parameter called the C penalty parameter, and as C gets above 1, the algorithm tries not to misclassify any point. So it tries to maybe stretch the line, especially with radial basis, tries to make very curvy lines for that stuff. So here's another article on that if you want. Some pros, it's once we have this set up, it's fast to classify. A con is it's sometimes slow with complex data sets. Sometimes the algorithm to find the best solution here takes a while. So sometimes you run sport vector machines and you just have to wait for hours for it to find a solution with complex data sets. It's more effective with higher dimensions. It's easier to find these lines. It works best if our data is scaled and normalized. So if we have data along the same size, if we have some data that's, because again, we're doing distances between it. So if we have some data that's measuring things in millimeters and other things in meters, or some points, very small decimal points and very large numbers, that doesn't work very well. So usually we have to scale our data for that. Okay, so those are the first two, support vector machines and nearest neighbors. The next is what is called a decision tree, and this is what kind of comes from the old expert systems we used to try to develop, where we'd ask experts, how do you decide something here, and how would you decide this? And what it tries to do is create a set of yes, no, true, false questions to differentiate things and set this up. So, and you can actually have it display this stuff. So you can give it the data and say, how would you break up this data? And the algorithm will say, well, first I'm going to, in this example, look at the pedal width and see if it's less than 0.8. And if so, it's this size. So basically, if I go back up here, it's looking at the pedal width here and saying anything below this line here is this sample. So that's really easy. So it'll do that. And then it'll say, well, but anything maybe above this size is green, anything below this. And so it tries to kind of divide this up into sections by doing these if-then things. So again, we might say if the pedal width is less than 0.8, then it's, we go down here and it's a setosa. Otherwise, we look at the pedal length and see if it's less than 0.475. And if so, we then check the pedal width, and if it's less than this, it's a versicolor, otherwise it's a virginica. If this pedal is greater than, then we look at this and we try to do that. So it breaks these down into a series of if-then questions. These rules are pretty easy to create with the data often. The data doesn't have to be scaled or normalized, but one problem is that this tends to overfit our data. It will find rules for every possible combination here, and so it sometimes overfits and becomes too specific for every point out there, and so it doesn't generalize sometimes very well. So. Now, a way to improve this is to combine multiple decision trees together. So we can do what is called a random forest. So again, if we have a decision tree, if you put a bunch of them together, you're going to get a forest, of course. So we're going to have a random forest here. We're going to have multiple decision trees. We're going to feed each tree some different data from our set. So we're not going to feed it all the data. We're going to feed each tree a subset of the data and have it make decisions there. And then once we have these different decision trees, then we can take new data and feed it in to each of these decision trees. Each decision tree has the results, and then we vote on it. And again, we're often having majority votes, so we'll have an odd number of trees here. And then they vote, and the answer that gets the most votes is given. So a decision tree, a random forest, is a random collection of multiple decision trees, each given a random subset of the data and voting for the correct answer. Now, this whole idea of combining weaker models into a stronger model gained traction and is goes under the heading often ensemble models. So we bring together an ensemble measure and we do some things called boosting. There's actually three different ways of combining models together: bagging, boosting, and stacking here. So let's just look at those. This sort of model is called bagging the decision tree. This bagging collects homogeneous weak models that are trained independently and vote for the best answer. So that's a random forest. So again, homogeneous means they're all the same types of models. They're all decision trees here. There's not a support vector machine in here. They're all decision trees. They're all independent. We train each one independent on a different set of the data, and then they vote on the best answer. Now, that's not always the best solution. So boosting is a way of combining models together that are trained sequentially. So we'll train one model, and then we'll look at the results, especially the training data that it got wrong. And then we'll retrain a new model and stress the data it got wrong for that, or fit it better. And then we'll create a new model there. So we'll create a series of models, but they are trained sequentially with an algorithm that tries to optimize their performance. So they get more complicated, and it's hard to explain how they're exactly working, but they again are proving these. These kind of algorithms have been winning a lot of the competitions like Kaggle and those sorts of competitions out there. Two of the common libraries out there for boosting are called AdaBoost and XGBoost. We'll be using XGBoost in our weekly exercises. So now one other model or ensemble we won't be using is called stacking. And again, this has gained use a lot lately. And this combines heterogeneous weak models to create a better model. Now, what do we mean by this heterogeneous? It means that they don't all have to be the same type. So we can have a support vector machine and a k-nearest neighbor and a decision trees, and have them all together, have them all working and voting, or making decisions, and somehow combining the results of those. So this is a nice format video, again, that kind of walks you through this if you want to watch that. So that's a quick overview of classification models and methods. So.